Hello and welcome back. In this video we'll continue with section 7.2 and we'll start by constructing a confidence interval for a population mean. So what we have here, listed below, are the weights of randomly selected girls at birth in hectograms, meaning hundreds of grams. So all those weights are listed down here. We see that there are 15 values, so there's 15 things in our sample, weights in our sample. The average is 30.9 and the standard deviation is 2.9. So we want to construct a 95% confidence interval for the mean weight. Now, before I really dive in here, most of our methods rely on some normality in the sample mean distributions. And we see that we only have 15 members in our sample, which means that the other requirement must be met. There are two requirements. Either the sample size is greater than 30, or the population itself must be normally distributed. So we will simply have to assume that the population, that is weights of girls at birth, is normally distributed. Once we assume that, we can essentially carry on. So we want to construct a confidence interval, 95% confidence interval. So the confidence interval itself is just going to be, we'll take our sample mean and we subtract our error, margin of error from that, and we will add our margin of error to that to come up with the lower and upper bounds for our population mean. So to do this, we will need to know what our error is, and the error in this case is going to be t sub alpha over 2 times the standard error divided by our sample size n. So what we know our sample size, we know our sample standard deviation. We will need to figure out t here. And in order to figure out t, we also need to know the degree of freedom. And because we have 15 members of our sample, our degree of freedom would be 14. So our 95% confidence interval means that alpha is going to be 0.05. So let's come over to StatCrunch. We'll open up our calculator for the t distribution, and we are looking at our degree of freedom is 14. We want to look to the right, and we want the area to the right over here to be 0.025, which is half of 5%. So we get a value of 2.14, and I'll round to 5. So let's write that down. Our t sub alpha over 2 is 2.145. So now we can calculate E. So our margin of error is going to be 2.145 times our sample standard deviation, which was 2.9, divided by the square root of the sample size, which is approximately 1.6. So now we can plug this in here, and our population mean should be between 30.9 minus 1.6 and 30.9 plus 1.6. Here this is 29.3, and our upper bound is going to be 32.5. So here is our 95% confidence interval. And to state explicitly what this means, we are 95% confident that the population mean is between these two values. If we want to be more confident, we would have to give a wider interval to capture more numbers so that we're more confident that is in there. But this will suit our purposes for this question. Now, since we know the actual values on our sample, we could use StatCrunch to come up with the confidence interval itself. So if we come back over to StatCrunch, we'll see that I have typed in all of the weights and I've labeled my column weights. So if I want to construct a confidence interval using the t statistic, I come to stats, I look at t-stats, I have one sample, and I want to calculate something with the data listed in this column. So I want to look at with data. I have to select which column this is in, which is the weights column. And it gives us a couple of things to perform. We can either perform a hypothesis test. This is not what we're doing. We'll do this in later chapters. What we want to do is a confidence interval. And again, the confidence level is going to be 0.95, so it's convenience is already there. We get to ignore the rest of this and click compute. So here are the values. So the variable were the weights of the baby girls. Our sample mean is 30.866 repeating. Okay. If we come back to our original question, so I got this directly from the book, and they said that the sample mean was 30.9. So they are not rounding here, which will mean that because we're rounding, we will come up with different answers. Their degree of freedom is the same, 15 minus 1. Their lower limit is 29.2, let's say round to 5, and their upper limit is 32.45. If we come back to ours, we had 29.3 and 32.5. That is pretty close to this. 29.3 and 32.5 are close to these, and the only difference would be the rounding that I did in my calculations. So this will give you a more exact answer. And in any case, you will always want to round to one more place than the data has. So the data is rounded to the nearest whole number. So when we are giving our confidence interval, we will want to round to one place past the decimal point. So two ways to construct confidence intervals: using our formula or plugging everything into StatCrunch. And we can take confidence intervals and learn a little bit more from them. So for instance, if we're given a confidence interval where we have our upper limit and lower limit for the confidence interval given, the sample mean should be the point exactly halfway between the upper limit and the lower limit. So we'll just take the upper limit plus the lower limit, and we'll divide by 2 to find the midpoint, exactly halfway in between. And one of the uses for the sample mean is it's a nice estimate for the population mean. It's an unbiased estimator. So if we just had to take a guess at what the population mean is, the sample mean is a good guess. The margin of error, again, if we think about the confidence interval sort of on this line, the margin of error is going to be half this distance, because of here is the sample mean, up here will be the sample mean plus E, and down here will be the sample mean minus E. So the whole length of the interval is twice the error. So the length of this is going to be the upper limit minus the lower limit, and we'll divide that by 2. So we can easily calculate the sample mean and the margin of error from a confidence interval. So for instance here, if this is our confidence interval from 10 to 26, we'll know that the sample mean from which this was calculated will be 26 plus 10 divided by 2. It will be 36 divided by 2 is 18. And we can see that 18 is halfway between 10 and 26. Also, the margin of error is going to be half the length of the interval. So 26 minus 10 divided by 2. 26 minus 10 is going to be 16 divided by 2 is 8. So this interval is 16 long, so half of that is going to be 8. So that's going to be our margin of error. And one use for confidence intervals is to compare values. So maybe you can look at a mean for a particular value and a mean for another value, and we want to see, can we tell those apart? So we can construct more than one confidence interval, and if we compare these, if the two confidence intervals do not overlap, as in we have one confidence interval down here and we have another confidence interval up here, we're confident that the mean that this confidence interval corresponds to, the mean is going to be somewhere in there. We don't know exactly where, but we're confident that it's down here. And we're confident that the mean of whatever value this refers to is going to be up there. So we're confident that they can't be the same. So we're confident that they are not equal. However, if two confidence intervals do overlap, so if we had one confidence interval here and one confidence interval here, the mean for the first data set could be here, and the mean for the second data set could be there. They could have the same mean. So if they do overlap, we can't say a whole lot. They could be equal. They might not be. The mean might be there, the mean might be there. But they could be equal. So to really illustrate this, there's an example in the book that looks at the presence of cotinine in smokers versus people that have been exposed to smoke from other smokers, or people that were just not exposed at all. And I think this is just the amount of cotinine in their system, in their blood. And we can see that, for instance, in smokers, the levels of cotinine will be between 150, I think it's something like milligrams in the blood, up to about 225. So we know that the average amount of cotinine is going to be way up here. Whereas for people that have only been exposed to secondhand smoke, the values will be between, let's say, 25 and a little bit over 100. And those that have not been exposed at all will be between 0 and 50. So we know that the mean for smokers, we're confident that the mean for smokers is going to be up here somewhere, but we don't know exactly where. Whereas for people that have just been exposed, or people that have not been exposed at all, these means could be equal. They could line up. Or the people that were exposed could have a mean that's up here instead. So when there's separation, when there is no overlap, we are confident that the means are not equal. When there is overlap, we can't tell. We can't say with confidence that the means are equal or are not equal. We simply don't know.